Good afternoon and welcome, everyone. My name is Sarah Monaco, and I am the Alumni Relations Officer with the Faculty of Applied Science and Engineering, as well as the Program Lead for the Skule Lunch and Learn series. I would like to thank all of you for kicking off the 2024-2025 Skule Lunch and Learn program with us today. It's so wonderful having you all join. Now, we have alumni tuning in from all over the world. We have guests joining from 5 different countries today, including Canada, Hong Kong, Jamaica, places within the United Kingdom, and the United States. Now, before starting today's presentation, I wish to acknowledge the land in which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still home to many Indigenous peoples from across Turtle Island, and we are so grateful to have the opportunity to work on this land. Now, I hope everyone is excited about today's presentation, as our guest speaker is the leading figure in microbiology and engineering, focused on improving indoor environments for better health outcomes. Now, our professor, their research aligns with U of T's pillars through the Defy Gravity campaign, focusing on enabling healthy lives and creating a sustainable future. Their work explores the indoor microbiome from bacteria, fungi, and viruses, and how poor air quality, driven by moisture and inadequate ventilation, can impact health. But by developing these solutions, and which Professor Sarah Haines will talk about more in her presentation, she addresses climate-related challenges, optimizing indoor environments to ultimately improve human well-being. Now, without further ado, it's my pleasure to introduce the cornerstone of our Skule Lunch and Learn community, our esteemed MC and chair of the program, Laurie Hevola. Laurie is not just an electrical engineering 65 graduate. He exemplifies dedication within our U of T engineering alumni network. For over a decade, he has skillfully led the Skule Lunch and Learn program, investing his time and expertise to create a dynamic environment for innovation and knowledge sharing. And throughout his tenure, he has remained steadfast in preserving the cherished traditions that make our gatherings so impactful. And with that, please join me in welcoming Laurie Hevola, who will now introduce our speaker for today's event. Thank you.
Thank you, Sierra, for your very kind introduction, as usual. It is my pleasure to welcome our guest speaker today, Professor Sarah Haines, who will discuss how we can engineer healthier and more sustainable indoor environments. Professor Haines is an assistant professor in the Department of Civil and Mineral Engineering and is the director of the Indoor Microbiology and Environmental Exposures Lab. Her interdisciplinary research integrates building science, engineering, and microbiology to analyze the connections between the built environment and human health. She uses cutting-edge microbiology techniques such as next-generation sequencing, metatranscriptomics, and bioinformatics to understand the impact of moisture on indoor environmental quality. Her work aids in understanding indoor exposures from microorganisms and chemicals, providing for a cleaner and sustainable indoor environment, particularly for our most vulnerable communities. And now, without further ado, please join me in welcoming our guest speaker, Professor Sarah Haines.
Hi, everyone. Thanks so much, Laurie. Thanks for having me. I'm so excited to be here. So I'm going to share my screen and we'll get started. So thanks, everyone. So happy to be here. I'm Professor Sarah Haines, as mentioned, and I'm going to be talking about engineering healthy and sustainable indoor built environments. And so you might see right here on your screen, oh, what's that? It's actually some carpet fibers with some little mold spores growing on them. So that's just a taste of some of the things we'll talk about today. But I am in the Civil and Mineral Engineering Department here at University of Toronto. I work in the Hub for Advancing Buildings. So it's a group of 4 faculty, myself, Professor Jeffrey Siegel, Professor Sanjay Lee, and Professor Marianne Tucci, where we're really looking at this interdisciplinary research, thinking about improving human health and comfort, equity and resilience, and carbon emissions in buildings. And so with that, you know, a lot of the work that I do is within this built environment. And I think when we think about the built environment, you know, humans are really the only known species that have really changed our habitat so much with these large structures, right? Building bridges and roadways and transit systems and waterways, right? As soon as you turn on your tap this morning to brush your teeth, wash your hands, that's all part of this built environment. But what my work is really focused on are these buildings, right? This concept, the built environment and what's going on in our buildings and in our houses. And so we can kind of look back, you know, at historically, we see this built environment changing over time, right? On a high level. This is the Toronto skyline in 1901 to 1930 to today, right? A really vast amount and just different kinds of buildings and indoor environments that we've created, right? So we have all of these different buildings. And as our built environment, the skyline has changed, as I mentioned, so has our buildings and so have our homes, where we're spending a lot of our time. So we see, you know, past, present, maybe future, different kinds of indoor environments that we can think about. I won't touch on it as much today, but I have done work with the International Space Station, which I think, you know, maybe that's our ultimate indoor environment, our space stations, and space shuttles and so on. But our buildings have changed, right? Our spaces, our indoor environments have changed. And so a lot of where we spend our time, maybe you've heard this statistic, 90% of our time we're spending indoors. And so if you think about it, I know not all of us are in Toronto right now, but if you went to U of T or you're an alumni, you know it can get cold here in the winter. And I think we're spending a lot of our time inside, right? So this idea of this changing indoor environment, where is this going, and how are we going to adapt for this future, particularly in the face of a changing climate, right? So this is where we're spending a lot of our time, and I think it's something that maybe we all started to think more about with COVID, and it came to the front of our minds with COVID when we were all in lockdown, but it is a really important space that I'm going to talk about more today. So what comes to mind, you know, when you think about indoor air quality? And I can let you kind of, you know, think about it yourself. But I think when I, you know, think about indoor air quality, start to think about VOCs, right? So potentially volatile organic compounds, those odors and smells as well in our indoor environments. Maybe smoke, maybe particulate matter, maybe candles. Maybe you think of candles. Or cooking emissions, right? Things in our indoor environment that maybe could be impacting our health. And a lot of the work that I do is focused more away from those chemical pollutants and more into those biological pollutants. So things like fungi, bacteria, and viruses. So these microbes, as we call them. And they're everywhere in our indoor environment. And so microbes, they're truly everywhere, and I don't want to freak anyone out, but they really are, and that's okay. And in a lot of instances, it's good, right? It's good. We need them to survive. We need them as part of our environment. And so they're on many different surfaces, on our food, on our skin, in our gut. Who had their kombucha today to help their gut? I haven't yet today, but I'm sure maybe you've heard of that. And we have this human microbiome, okay? So we have a human microbiome. We are, when you're first born, you're coated in different microorganisms, and that stays with us. It can change, but it really stays with us. And this is that, you know, what we're taking along with us. We also have microorganisms that are extremophiles, and they live at the bottom of the ocean. They can live in bottom of the ocean where it's super hot by volcanic wells there, or you know, out in really cold, extreme environments. Okay, they can survive anywhere, which could maybe be scary, but it's also really interesting. And so when we have all these different microbiomes, we have our human microbiome, we also have our indoor microbiome. And so we as people, we are really large indicators of our indoor microbiome. And you may be looking at this graph and going, oh no, Sarah, why did you put, what is this? We're talking about microorganisms, what is this graph? And what this is really showing, all you have to see here are all of those different colors are a different home environment. And all of the little dots on that chart are different levels of humidity, but they were all samples taken from a different home, and those are all the microbiome. So it's representing that microbiome information, what kind of species were in that home, okay? What kind of fungus was in that home? And what we were finding was really, different homes are very similar to each other. Just like your human microbiome will be very specific to you compared to someone else. So when we are in our homes, in our environments, we are populating that space. We are creating that microbiome within that space. And depending on your home, so your home environment is different than someone else's, is different than someone else's. And there's been studies done where they've actually tracked those microorganisms throughout as people moved, and they will see, when a family moves, they'll kind of populate that new home with their previous microbiome. Okay, so we're creating these different spaces, but it's not just us. Okay, it's not just us. It's also many different things, right, that are coming and creating this indoor microbiome. So we can have fungi, and so when I say fungi, I'm talking about molds and bacteria that can come in through outside air, so leaving windows open. We can track them in when we walk around. Your pets as well, they go outside, they come back inside, things like plants. And then also, active indoor mold growth, which ideally you don't have, but we'll talk about a little bit more. And this is really what's creating this indoor microbiome space. And not all of it is bad. Some of it can be helpful, some of it could be harmful, but it is this space. And we know that these exposures can create and lead to harmful health implications, right? So potentially these different indoor exposures, being exposed to high levels of mold and moisture, potentially high levels of particulate matter, this can lead to respiratory diseases, things like asthma, increased coughs, headaches, and so on, that could, be harmful to our health. And I do want to say right now, something that you may be thinking of as we're talking about mold, and we can talk more about it during the Q&A. This association between being exposed to mold and human health outcomes, we still don't know where that linkage is. So we know that people could be exposed to these molds, and then we're seeing this outcome, but we don't know that causal link. Talk more about that as well. So how are we going to prevent all these exposures that I talked about? We talked a little bit about mold, some bacteria. I think the big indoor environmental exposure that maybe was on everyone's mind, and hopefully we're not sick of talking about it, was COVID, right? And preparing for potential future pandemics. How are we going to prevent these indoor environmental exposures? And so one way that we had initially, been thinking about this and preventing this exposure to viruses was with transparent barriers, right? So maybe you went to the store or you went somewhere and you saw these barriers, but some of the research was finding that they might actually interfere with our normal ventilation that would be helpful in preventing those exposures. So by putting up those plastic barriers, this research was seeing, well, actually we're seeing potentially more clustering of where the virus is, and it's not really dissipating the way that we would want through ventilation. So with those barriers present, it could increase the potential exposure or, not interfere with our normal ventilation. So some ideas of things that other researchers have been doing are, maybe instead of using plastic barriers, we use things like high flow air extraction. And so in this research, we can kind of see here, maybe it's something where we actually have, some kind of, there you go, you can see that, but they're looking at the cough and how that's being dissipated by ventilation systems. Maybe you have, your own ventilation right there next to you that's being helpful to, get rid of and dissipate these different particulate matter and viruses. So maybe this could be a different method that we can use. But one thing that I'll really focus on is indoor air filtration. So something that a lot of my research has been focusing on is, can we use, portable air cleaners to, create and prevent these kind of exposures if we do it effectively. So using air filtration, which I mean by filtration, is when we're actually filtering out those particles. So filtering out those viral particles or particulate matter and so on, and getting rid of that in our indoor spaces. So we use that through filters, right? We have a flow, and we're pulling that the air through and collecting that material onto these filters. And maybe some of you had actually built, you can see on the right, the DIY air cleaners. I don't know if anyone has built any. I did. They're really fun to make, really easy to make, and actually may be more effective than some of those very expensive affordable air cleaners that you can buy in the store. So there's been some studies on that, looking into, how effective they are if they're built correctly. So a low-cost way to, increase ventilation, increase filtration, and create, potentially use this to decrease your exposures. And this has actually been shown in a couple of different papers, but one I'll show here, where they were using these air cleaners to reduce the airborne viral concentrations and loads in indoor spaces. And so on this graph, you see the residences along the x-axis, and then the CT values, which that would be in microbiology language, kind of the concentration. You could think of it as like, so the concentration, so higher would be more. And you see in the primary room, so that would be the sham period when there wasn't any air cleaner in there. And then to plot B, where we're seeing where there was filtration, and we're seeing that decrease, right? We're seeing a decrease when filters were added and they're appropriately sized. Maybe we can use them to reduce these exposures. So ventilation strategies and filtration strategies can reduce viral particulate concentrations. I think it's really important to think about things that are building specific and what people need, right? And these portable air cleaners could be low-cost methods of really reducing these indoor airborne transmissions, especially if we're thinking about in the future with potential further pandemics and so on and so forth, and just decreasing our means of exposure could be through these strategies. But they can also be used to study viral presence. And so this is where my research was really getting into, can we use these portable air cleaners to understand what's in our indoor environment? And so dust is a really great substrate for understanding our indoor microbiome. What kind of viruses, what kind of bacteria, what kind of fungus, or how much is there? And so dust is full of lots of different things. A lot of it is your skin cells, but it's a lot of other things too, as well as chemicals, as phthalates and flame retardants. They're also in these samples. And we see, dust, a lot of this exposure. I have on the right here, this idea of resuspension. And so our dust is collecting lots of different components in our indoor environment, and it could sometimes get resuspended back into the air. And so some research has really looked at, crawling babies while crawling on the floor. How much are they exposed to this dust? What's in it? And how often, and how is this getting resuspended into the air? And I didn't include it, but you should go look up this study, because they did build a robot baby to test, so they didn't have actual babies crawling around on the floor. They have a robot baby that they were looking at exposures to the indoor particulate matter and dust. But in my lab, we use dust and DNA and RNA-based methods to really understand what's happening in our indoor environment. And so we can actually take samples of dust, we can DNA extract that dust and to get, what is in there. So the DNA, the RNA, we can collect that, and we can run that on something called quantitative polymerase chain reaction, qPCR, or digital PCR. And you may be going, ding, ding, I recognize PCR. Probably during COVID, you might have had a PCR test. It's really the same concept, same thing. We can search for COVID. We can take, if you remember, you did a little nose swab, you sent it in, they did a PCR test. We're doing the same thing, but with dust, really. We're going to take that dust, run it through the PCR machine, and understand, was there COVID there? Was there fungus there? Was there a bacteria there? We're looking at all those different things. And that's going to tell us how much. It's going to tell us, was it there and how much was there? How much DNA from that specific species or type of virus was there? We can also use sequencing techniques. The sequencing techniques will really tell us about what was there. So PCR will tell us how much, and then sequencing will tell us, what was there if we don't know, right? So maybe we have this dust. I'm not sure what's in it. I don't know what kind of fungal species are in this dust sample I've collected. We can use sequencing to really help us understand, okay, what was there? Right? What are we seeing? Are there specific genuses and so on? And then there's lots of processing that goes into it. So it's going to tell us how much and what is there. And so with using dust, we may be able to use this, and what we're finding is using it as a monitor for viral RNA presence in indoor spaces. So this was some work that I was involved in previously, where we were looking at taking different samples in an isolation room. So this was where someone was positive for COVID. They were isolating in a space, and we took different samples, from their desk, from the bathroom, from their floor dust, their tables. And what we were finding was that the most viral RNA that we were detecting, you can kind of see from this figure, was in that floor dust. It's the darker color. That means higher concentration. So we're seeing more viral RNA in the dust. So that means, okay, maybe we could use this dust to really understand and monitor these spaces even before we knew someone was positive, right? Maybe we can use this dust if we're testing it to understand. So our idea, we link back to what I was talking about previously about portable air cleaners. Can we use this portable air cleaners as a way to understand how much viral RNA or other, maybe it's RNA of bacteria or fungus or whatnot, other microbes are in our air? And so we can use here's a little engineering for you. We can use this idea of quantitative filter forensics. What does that mean? It's really taking what we know about a filter and being able to back calculate what was the concentration of what we're looking at, what was in this case, SARS-CoV-2 RNA, how much was on there, using the mass of the dust, the flow rate through the filter, how efficient that filter was, how long it was running, and then taking that and equating and determining, okay, what was that concentration in the air, right? Because we have the flow rate, we can know this is how much was in the air at that time. And I do want to note right now, in case I get a question, this is just RNA, so we don't know if it's infectious. So that would be a different kind of test that we would need to do. This is just telling us it was there, right? It was present. And so in this study, we actually deployed portable air cleaners in indoor spaces. This was a study done by my PhD student, Zoe Hoskins, and in collaboration with Professor Jeffrey Siegel, who's a colleague, where we were deploying these portable air cleaners. That's what that is, the little black air cleaner. And then we had this filter paper that we would put inside. Zoe deployed these in homes and classrooms at U of T, in different dining locations. During when it was more active, SARS-CoV-2 was happening I think 2 years ago now. And she would vacuum that dust off those filters and then run that process that I described earlier, where you're taking the dust, you're DNA extracting it, and then we're looking at, what was in it. And what we found were that concentrations, we can use this, right? We were seeing, okay, we actually can vacuum this off of a filter, which we really were, unsure. Is this going to work? Would there still be RNA present, right? Would it have decayed? No, it was working. So we can vacuum it off a filter. And what we're seeing here is that depending on where you were in a house, there is a decrease in this concentration. So we see on the x-axis, you have an isolation room. So that was where the person was isolating. We have the hallway. This would have been right outside of their isolation room. And then a living area. So we had a filter down in the living space. And on the y-axis, we see airborne concentration. So this would be just RNA copies, what we're getting off of that PCR machine, how much RNA was present. And we see this decrease. And you might see that we have these two figures. So the first figure includes house A. The second figure doesn't include house A. And that's so that you can see this decrease, because whoever was in house A must have been a super spreader, because they were just had so much, we were getting so much viral RNA from their filter that was in their room. So you can kind of see that as you move away, this really shows us, and they were isolating in these rooms that potentially, this dust, this SARS-CoV-2, it was getting throughout the house. Concentrations also varied across sample sites. So we see when we're looking at, you see the first three on that x-axis, that's from the homes, but then we also looked at classrooms and dining locations, and it was really variable across these classrooms. And for the classrooms, we didn't know, who was there, if anyone was positive, but we were detecting SARS-CoV-2 in these classrooms. So I really think about this, it's important to think about these methods as potential non-invasive, no compliance needed environmental surveillance, right? If we have portable air cleaners or filters in buildings, in our homes, maybe long-term care settings or schools, they could be used. And we're testing that every so often to determine, is there going to be an outbreak, and looking at this kind of environmental surveillance over a long term. And right now, my student is looking to detect other viruses, bacteria, and fungi using this method, so we can understand what's in our indoor air. Okay, so what about mold exposures, though? So we talked a little bit about viruses. Now let's go back to this idea of mold and fungi. And so when we're in our indoor environments, mold really loves moisture. And so with increasing moisture, there's increasing fungal growth. And you may already know this from, maybe you've seen in your bathroom, perhaps. I know I've talked to a lot of people in the area where you've seen mold kind of growing along your shower. It loves moisture, right? And so this was some work that I did a while back with a colleague looking at mold growth on carpet. So we're back to we're back here. But this was increasing as you increase the relative humidity, as you increase that access to moisture. So 50% relative humidity, 85% relative humidity, 90% relative humidity. That's what those correspond to. You're increasing this humidity, you start to see this increased growth. And this was specifically in carpets, but we see this in many situations, right? So as you're increasing the amount of moisture that is available for these species, they get really excited and they start growing. And you can see that even more in this differentiation. So we see that it also depends on the material. So mold on carpets and carpet dust actually increases kind of, it's not a lot going on until it reaches about 80%. On our y-axis here, we have that relative humidity condition increasing from 50 to 95%. And then our y-axis, again, would be that concentration of growth. And once you reach about 80%, you start to see this increase. For drywall, which is in figure B, you're really not seeing that growth until it's really, really high moisture, high humidity conditions, about 95%. So once we're getting that really increased moisture, we're seeing that increase in growth. And so again, they really love they love the moisture, but it does depend on the material and the substrate and what they're using. And so I think there's this concern over this mold and moisture, one, because of health concerns, but also degradation of materials. And so molds can, cause wood rotting, dry rot. They can even grow on concrete and marble, right? These species, I talked about it at the beginning, microbes are very durable. They find a way to survive. And so they may be, contributing to this degradation of materials. And so some of my other work has really been focused on looking at mold and moisture and the way it impacts communities and our First Nations communities. And so this is just some images taken from different communities in Canada where we're seeing really heavy instances of mold and moisture, and this increase of this occurring potentially due to, you know, inadequate ventilation or strategies to really mitigate mold and many other systematic issues that, you know, we can also discuss. So this is something where my research has taken me to really collaborate on these issues. And so I have been working with a group of researchers from building science, social sciences, public policy, health sciences to discuss you know, how do we co-develop solutions for this issue of mold in First Nations housing, as well as, you know, some other issues that we're seeing within housing. And so we've brought in government organizations as well. So Housing Northwest Territories, Nunavut Housing. We have about 10 Indigenous communities that are part of this program from Harvest to House, spanning from Saskatchewan to Northwest Territories. And through this, we're really looking at, you know, what can we solutionize together? And I think that's a really important piece that I want to bring into this is, you know, as engineers, I think a lot of us sometimes have that idea of, oh, I have a solution, I've engineered a solution, let's go implement it. For a lot of community-based work, that's just not the way that it's going to work and not the way that it should work. And so what we're really doing is working together with our communities, with our partner communities, to establish pathways towards change, pathways towards how can we work together, what kind of solutions would work for a community, what can be done to alleviate some of these instances of mold and moisture. And I want to also call out, you know, there's also instances of overcrowding as well, which is contributing to these increases of moisture, and just inadequate and not enough housing, right, in many of these communities that maybe we don't talk about or realize is happening within many of our communities in the north. But this is something that my team or our team is really working on, and really working with our community champions who are trying to push this forward. So right now, at this stage, we've done mainly just mobilizing with communities. We've worked with them, held many workshops to kind of create these relationships. And now we're mobilizing the communities to collect data, right? So we want to look at this indoor air quality in these homes and think about the IAQ measurements. So things like CO2 and relative humidity, getting the temperature, the particulate matter, as well as interior imaging. So we've actually done some imaging where we go in and can visualize the mold, see what's there, and collecting dust. So we understand, you know, how much is there, what could they potentially be exposed to. And we've done some drone imaging as well to just see, you know, what is the extent of these issues, and how are all of this building science kind of relating into our indoor environment. And so these are just some photos of some of the work we have someone flying with the drone. We did blower door tests. I know I'm keeping it mainly to the indoor environment and not as much building science, but that's definitely something where we're looking at, you know, the building enclosure and how's all that working. And so as part of this entire project, we've also started to look into different kinds of building materials. So one of our community champions, Natalie Kleik, she is actually working to found this Indigenous and woman-owned company called Rocktree MGO board, where she's looking at, you know, can we use different kinds of materials that maybe are more readily available in the north to combat this mold issue. And so magnesium oxide, it's a composite board. It's made with gypsum and cement. So it's a gypsum and cement board alternative. So it'd be an alternative to drywall. And it's touted as being more moisture and thermally resistant as well. And so what we've been looking into with my team, our research team, is, you know, how could MGO be used? Does this make sense? Is it actually anti-mold resistant? Is it antimicrobial? Can we actually see these results, and does this really work? And so some of the positives of this MGO board would be that magnesium is readily available in Canada. So we actually have magnesium deposits in Canada, so it could be sourced locally. And it uses different wood chips and things that could also be sourced locally. So there's potential alternatives to creating a material that could be, leveraged by communities and created by communities. So that's something that we're currently looking into. I wish I had more data to show you on that, but it's still kind of in the early phases and a potentially, very exciting process and project. Final note, I have a student who's looking at a different kind of material and thinking about coatings. So could we use different kinds of coatings on our drywall that could be, anti-mold, or be, not anti-mold, but less likely to grow mold, right? So this is this idea of using these PDMS brushes. So PDMS, you may have heard of it. It is an alternative to PFAS, which you probably maybe have heard of before. It's the forever chemical that's now within all of us, and it has been banned in many places. It is toxic, so this is an alternative to that. It's a it's non-toxic, environmentally friendly, but it is it can repel it can repel moisture. It can repel liquids. And so it does a really good job at repelling liquids. So PFAS had traditionally been on, your anti-stick coatings, your pans that were anti-stick, your rain jacket that maybe, the water beads off of. That's things that PFAS would be on. So they've created a new, we've been working with some folks in engineering who are designing this new kind of coating with PDMS. And so our idea was, well, could we put PDMS on building materials, and could that be helpful, right? With this kind of, flexibility with this material, could we put this on, could we put this on that material, and it would be, antimicrobial. So we did do that. We coated it onto drywall. So we just had regular drywall, and then we coated that PDMS brush coating onto the drywall as well. And you can kind of see the results, maybe not as much as what we had hoped. So on normal drywall, you can still see a lot of mold growth. With the coating, we're also still seeing a lot of mold growth. And so even after 21 days of incubating these drywall samples at really high humidity levels, the untreated drywall showed significant growth, but also did the one with the PDMS brushes. And I think this was something we really didn't know. We weren't sure if having something that repelled liquid, would that be helpful? Would that be useful in this environment? And what we're seeing is most likely no. So having a type of coating that repels liquids started to actually, what we're hypothesizing, creating little microenvironments. I said mold likes moisture, and so it's creating these little environments where the mold was just, it had lots of moisture right at the surface, so it can start to grow. And so it was maybe not getting down into the material, but it was sitting right there at the top, and potentially increasing that mold growth. And so with this, we actually can see with the PDMS treated drywall, it did have the most. So the D, it would just be drywall. So I would focus on that one. We're seeing that increase in growth, and then the DMP would be with that coating, and we're seeing, it also had an increased growth as well. So sometimes in research, I think it's a valuable lesson. Sometimes you try something and it doesn't work. And it was, an interesting question, but we're going to be further looking into, other materials. Is there a way that this could work? Could it work on other things? We've been thinking about it on masks. So that was actually a discussion on, could it be actually more useful coating on masks, not really on building materials, and so on. Okay, with that, how do we engineer healthy, sustainable indoor environments? I really think they're through community-driven building designs and science-based approaches. So really, if we understand the science behind, how we are exposed to these different microorganisms, microbes within our indoor environment, we can then, develop these sound approaches, and working directly with communities and community members, we can build better solutions. So with that, I would like to thank my whole team, my Indoor Microbiology and Environmental Exposures Lab, as well as the Hub for Advancing Buildings team, and all of our many sponsors and funders. So thanks so much, everyone.
Before I close, I would like to thank Professor Sarah Haines for being with us today. Thank you for such an informative and interesting presentation on the impact of indoor air quality on human health and how engineering and microbiology can address challenges in vulnerable communities. And as we've seen from the questions, it is a topic that is of considerable interest to all of us. To everyone who joined us here today, we invite you to share your feedback on the Skule Lunch and Learn series. A link to the online survey is in the chat box at the bottom of your screen, and will also be shared with all of you after this event. Also, a link to the presentation will also be shared with all those guests who registered earlier this week. Skule Lunch and Learn events are traditionally hosted on the second Wednesday of each month. Thus, our next Skule Lunch and Learn event will feature Professor Yu Zhu on Wednesday, November 13th, again at noon. Professor Zhu will discuss metal additive manufacturing from 3D printing to industrial applications. In closing, I would like to thank all of you from around the world for joining us for today's presentation. With this, I hereby adjourn our first Skule and Lunch and Learn event of the 24-25 program year, and I hope you can join us for future sessions as well. May all of you have a wonderful rest of your week, and see you all again next month here online. Thank you and goodbye.